I'm trying kind of to bring things back kind of together. What we have talked so far, we talked about the projective space. And in the projective space, just to remind you, it's practically the projection of a 3D world coordinate into a plane. And then this plane will be practically what we call the projective space. Then we looked into transformation between the mathematics of these transformation between various projective spaces. And then we look into the hierarchy of these projections. And if any of you have any question, we can always kind of come back and talk about these things. But what I'm going to talk today about is a single view geometry, practically how we deal with the camera and images. And I assume I will talk about the camera model in this lecture. And the calibration, maybe I'll touch a little bit in calibration, but I will continue for the next lecture. And then I'll move to a two-view, or what we call dual view, where we will show how we can actually reconstruct a 3D information or depth values from two images when we have a correspondence. So when we look about like image, so wait a minute, okay. This is, so before I go, I think I want this slide to be before that one. Just a little bit about the history of camera and where it's actually started. One of the things which is interesting is Aristotle talked about the issue of imaging 330 BC, and the issue which his was interesting, why the image of from even the light of the sun will cast a circular shade, even so like rectangle square. This was his main concern, and this is the first actually person who started to question the issue of the pinhole camera. One thing which is even was pretty much not touched until, at least as far as of my knowledge, this is until a kind of a mathematicians or physicist who lived he was born actually in Iraq and lived most of his life in Cairo. And this is the first one actually created the idea of the pinhole camera, what we actually know it today. And the word actually camera actually came from the word in Arabic which is called qumra, which is actually a dark room with a hole inside. This is he developed most of the first one to develop the mathematics of this. And the way he developed this actually is a very interesting story. He was a famous mathematician who lived in Iraq. He was born in Basra, and he was like saying he was good in mathematics and physics, and he said, if I have an idea how actually to prevent the flooding of the Nilus, and I control it, if I were in Cairo, I'll be able to do it. So then the Khalifa at that time heard about this story, and so invite him to come to Cairo to implement his idea to prevent the flooding of the Nilus. And what happened with actually it should be in English, the Nile, yes? Okay. So the Nile, and then he actually was supposed to build a dam where actually there is one dam in Egypt today. But then after a while, he realized that it's impossible to do it with the technology of his time. But he was afraid that from the Khalifa at that time that he's kind of will not be able to deliver what he was promising. So he's actually pretend that he was crazy, and in order kind of to not to get his punish. And then at that time, it's not really clear why, but the Khalifa actually ordered him to stay in one of the palaces and not to leave it at all, kind of a house prison. And this is where he developed all the mathematics of the pinhole camera. It's kind of interesting because he was pretty much in kind of like a home prison where he developed this. So this is where actually the source of the original mathematics of the pinhole camera. And if we look at the pinhole camera as we know it today, it's practically, we think about like two coordinate systems. Or let us look at the simple case where we have actually the XYZ, and then we have the image plane, where practically any point X will have an image X small in the image plane. And this is not that this can practically the line which is called going to the camera center. Now, if we think about this kind of like try to think about like a similar triangle, it's very easy to kind of develop the equation based on the distance of the focal point, where we assume the image plane will be in the focal point, and then we will think about these kind of like distances if the coordinate of the point is x, y, z, and then we can easily know that this is practically a transformation from x, y, z point in the world coordinate. Okay. You can take this, it's practically. So this is the transformation, which is practically, this is the transformation we're thinking about. If we move to homogeneous coordinates, which we expect into x, y, z to be the point in the image plane, which is what we will see that this is practically this matrix multiplication. This is, from this point it's very simple, which is if we take this is we fx, fy, and z, and then if we write it as matrix notation, this is what we will get. Now, if we think about this, now we will have this practically the transformation, the camera transformation, or we can write it as P, where P is the camera transformation, and then we have X big is actually the world coordinate, and then X small will be the image plane coordinate. Okay, so if we think about this kind of notation, we can write now this is what we are interested in, is actually what we call the projective transformation, which will take a world coordinate x big into small like the image coordinate. So that the x, which is the x, y, z, and the x small will be x, y, and what? And f. Or actually, we can remove this if we're talking about the image plane. It should be x, y, 1 in the 2D coordinate system. We can practically also write this mathematically as the diagonal, which is f1. This is exactly what we see on top, and the I, which is the unit matrix in the. This is pretty much very simple notation, which is often used. Now, if we think about this as what we call the original coordinate in the image plane, what we call if we think about this transformation and go back into the coordinate system we have, just take a look at this image. So we have the principal axis, we have the camera center, and we have the image plane. Now there is one which is called the principal point. The principal point is the intersection of the principal axis with the image plane. So if we think about this, so if we think about this is what we will get in the camera coordinate. But usually the principal point may not be at the origin, or may not be actually along the principal axis. It could be translated a little bit kind of in different, like have kind of a shift. And in this case, the shift will make, instead of having the principal point at the origin, it will be at some point x0, y0. And this is easy, can be actually injected into the matrix. It will be very simple, because the point will be, instead of fx, fy, and z, it will be fx plus zp and zy. And in this case, what we will get, we will be able to write this coordinate as this form. So this is what we will get. So pretty much what we have done is actually shifting the coordinate to bring the two coordinates together, which is mean now what we will have, the starting case or the simple case, we have the camera and the world coordinate are the same. Now, what I said that the camera coordinate and the world coordinate may not be the same. If we assume, let us ignore that the camera just have a little bit of shift over the, which is mean that the principal axis will not go through the origin. In this case, what we will be able to correct that by creating kind of different camera coordinate, which is one will be for the camera coordinate and one will be the world coordinate, and we can bring them back together by a small translation, which is actually, if we think about the xp, x0, y0, we can do the translation to make these 2 points actually coming to the same world coordinate. Is that point clear? Now, and this is often we write this as the camera coordinate system, and we can write this as the translation of the camera coordinate, which is what we have from what we saw before. And this is the matrix K multiplied by I and 0. Now, if we're thinking about this is the I, this is the unit matrix, and this is the 0, we have this. Pretty much the K will be kind of like similar to this. Actually, will be exactly the shape of K. And often this is called the camera matrix. Often it's called the calibration matrix or the camera intrinsic parameters. But this is what we actually will go and see how to find this. But this is one way to be able to get the parameter of the camera and separate them from the transformation. Now, but the camera may not be only shifted a little bit, which is mean the difference between the world coordinate and the camera coordinate may not be only a shift, because we know that if this is the world coordinate somewhere here, the camera may not be not only the same kind of a translation, they encounter maybe another rotation. And this is what we will have here. So if we have this is the world coordinate, in order to bring the world coordinate to the camera coordinate, we only need to do pretty translation, but also we need rotation in order to align the two coordinate system. And this is practically the transformation that will bring the world coordinate into the camera coordinate. So this is what we will, if this is the world coordinate and this is the shift we have, and this is the rotation applied to this point, and this is how we will be able to get into the camera coordinate. So this is a rotation matrix what we know, because this is 3 by 3 rotation, typical rotation matrix. So I can actually write this a little bit different, which is this is the point x, y, z, the world coordinate, and this is a block kind of block kind of matrix, which is mean this is, in this case, we'll have this as rotation matrix, and this is actually just multiplying this inside, and this is the rotation matrix. And we take this x outside, and this is the remain of the matrix. So we can write this very simple, as this is the point here, and pretty much this is the matrix we have. And now we write it in kind of a simple compact notation, as this is the world coordinate system. This is the translation we have in the camera position. This is the rotation, which is we have applied to the camera. We often refer to this part as the viewing matrix. In many kind of many computer graphics kind of APIs refer to this as the viewing matrix, and this will be kind of the parameters of the camera. So we have the viewing matrix, which is pretty much the transformation that bring the camera into the canonical position, or it's actually combine or bring the points or bring the points of the world coordinate into the camera coordinate. You can actually think about them as the same. So if we can write this, all this together, this is our actually projection matrix, which involve the parametric of the camera, the translation or actually of the coordinate system to match the camera coordinate system. Or we can write this in a different way as actually taking this, if we take this as the camera coordinate system, it's pretty much only we need to encounter the projection which depends only in the camera. But this is encode inside it, the translation and the rotation. So this is how we actually will bring the camera. So this operation guarantees that the world coordinate brought into unified kind of image coordinate system, and then a projection is applied. This is how we perceive the camera operation. So this is, if we think about this as in a general case, what we will get when today is like it's common to have a CCD cameras, which is what we will get practically the same matrix. When we want to calibrate or find what's really the metric, the projection, or the matrix that represent this camera, we can write it in a general term as alpha x, alpha y, px, py, and 1. This is often the case that we see these kind of like a calibration matrix. After the calibration, the only we need to compute this part where px and py is the translation. Now, if we think about this, often when we do the calibration, we get another parameter. We get here 0, 0, 0, and here we may get s, which is very rare. Usually, we don't get 0. We get small numbers instead of 0, and instead of s, we get small number. Very rare we find s different than 0 or below some epsilon that we can actually assume it's 0. That means there is a skew in the CCDs, which is very rare, but it could happen if they kind of some problem with the optics of the camera or the CD of the camera, which is mean that the x and y axis of the CCDs are not orthogonal, which is rare unless there is problem with the optics. So I kind of like it's very hard to see why they will create kind of non-orthogonal CCD. But this is pretty much how we will be able to look into this. And if we look at this matrix now, which is what we are talking about, very simple matrices. This is pretty much 3x4 matrix, and all these are 3x3 matrices. So if we think about these matrices, eventually how many degrees of freedom we will have? What? 11. Okay, where this 11 came from? From the board. Now, but think about this. We have the px and py. This is 2 degrees of freedom. We have the alpha x and alpha y. We have 4. What else we have? Which is the f, which is give us the scale, yes? And then we have the s, which is we assume here we will have. And there is another parameters which is we have.
Do you include radial distortion in your...
We have the rotation. All these parameters, we get them from K. So in K, we have 5 parameters. Yes, 1, 2, 3, 4, 5. Now the rotation, we'll have rotation parameters. What parameter will have in the rotation? It's actually, you will have 3 angles, if we want kind of to think about this. How many we have already?
Is it omega phi kappa?
Yeah, if we like the general case, we'll have 3. Yes, this is what will give us. This is plus 5. Then will give us 8. So where's the rest came from? Translation, which is x, y, and z translation. This is where we'll get 11. Is that clear? So we have 11 degrees of freedom. Now, the question which is up here, now before that, which is mean in order to be able to compute the parameter of the camera, we need to resolve 11 degrees of freedom, which is, if we think about it, usually what we have a point in the world coordinate and its image in the image plane. Yes? So this is how many degrees of freedom this will contribute. We know the correspondence. Someone give us the image of this point is here in the image. The image of this point in this. One correspondence, which is image in x in the world coordinate, point in the world coordinate, which is x and y and z, and point in the image coordinate. How many degrees of freedom will give us? No, one point. One point, if I'm going to think about 1 point, how many, maybe we'll phrase it differently, how many concentrate this correspondence will contribute? If I write it, how many equations it will contribute? So let us go back. If I take 1 point here, which is mean if I take 1 point not here, if I take 1 point here, which I know, which is I take 1 point here, which is a world coordinate, and then it will give me a point in the image plane, which is, I know this is any point in the world coordinate, which is be x, y, z, and 1. And this will be a point in the image plane, which will be x, y, and f, and 1. Yes? So if I write this as an equation, how many equations I will be able to extract from this correspondence? One could think we could extract 3 equations. Normal, yes, because we have x, y, and z. But practically, because of the f, and we are only looking for the correspondence up to scale factor, y up to scale factor, because sometimes even the 2 images, if I have the camera here and I move the camera along some axis, I'll get the same image. Yes? So this is why we will be able to get up to scale factor. So in this, since we are getting up to scale factor, we will realize that these 3 equations are not independent. Which is mean if I'm going to simplify them, I will end up with 2 equations. Or in other words, 1 equation could be created by linear combination of the other 2. So eventually, every point will contribute to 2 equations, which can satisfy 2 degrees of freedom. Now, in order to get 11, I need 5.5 points, which mean I will need 6 points at least in order to be able to resolve this equation. Now we'll go into back when we talk about the calibration, how we do that. But which is we have similar to how we actually recover the projective transformation. Now let us look more into the kind of some parameters of the camera, which we will use. So if we think about the camera, we have some kind of terms, which is maybe it will be, if we agree on these terms and understand them, will make kind of the explanation simpler. So we have the camera center, in this case, which is C. It's often if we are thinking about the camera coordinate system, often will be in the origin of the camera, of the coordinate system of the camera. We have the image plane, which is what we have just mentioned. And then we have the principal axis, which is the line connecting the camera center and perpendicular to the image plane. And then we have the principal point, which is the point P, which is the intersection of the principal axis and the image plane. Now, what we are interested, or the typical projection, which is interesting to us, is projection of x, which is any point in the world coordinate, to the point x on the image plane. So if we think about this transformation, like what we will get, like the camera center, C is practically, if we think about this as, and we writing this as a point in the 3D world, and we're thinking about homogeneous coordinate, we'll get a vector of 4, which is mean 1 will be the last value, and then we'll have x, y, z, or x, y, z, and 1. And we want this. Why we want this? This is the point which is its transformation will bring us to 0, which is mean PC equals 0. This is the camera center, yes? Because if we think about this is the origin, and now the transformation, any point which transformation will be 0, this is how it will call to the point which is all the projection will be 0, will be the camera center. Now, if we think about like a C containing any another point, let us look at not C, but look at another point, which is we project this into the image and actually giving us the value 0, which is mean not only the projection of not only C, projection of C give us 0, but actually there are many points which is along this line could give us a 0. Which is mean if we think about like any line which is connect 2 points A and C, this is pretty much parametric. This is parametric representation of a line. This is, anyone like kind of want me to just kind of go over what we mean parametric representation of a line? Okay, so this is a parametric representation of a line. If we assume the point x, which is will be a point on this line, the projection will give us x. Any point on this line also will give us the point x, which is, I think it's obvious. That mean the projection not only of that point x will give us x image, x small will be the image of all the points along this line. And this is one of the things which is, if we are going to back into inverse projection, for each point x, it could be an image of infinite number of points. Okay, and so this is exactly what's explained in this. And if we assume this is the center of the point is 0, this will give us the two kind of a camera types. One we called finite camera and one point called infinite camera. Both actually depends where the center of the camera exists. If the center of the camera exists in the finite point or infinite point. And the difference between them is very simple. Now, if we think about now the column and the row vectors, which is represent the camera matrix, instead of writing as a one matrix, we can write this as a set of column vectors, which is often kind of simplify just the notation. You know, all these matrices and all these vectors, it's maybe look a lot of symbols, but we are talking about matrix 4 by 4 or 4 by 3 or 3 by 3, and the vectors not more than 3, then not more than 4 values. Just pretty much we're talking about simple algebra. So if we write them instead of this matrix, we write them as a P1, P2, P4. This will be the representation of the column of the projection matrix P. Now, then what we will call P1, P2, and P3 are vanishing point. And now we'll see what we call by the vanishing point corresponding to X and Y and Z axis. What does that mean? That if we know that the projection, if we are going to like take, this is the image plane somewhere, the projection of this axis, because after rotation and transformation, will give us some like point here and some point here. And remember, every point here is a vector practically. And so this is, it's pretty much easy to understand or to see how this, where this came from. Because think about the axis X, it will be 1, 0, 0, 0. This is the representation of the x-axis. If I multiply this by the matrix P and just write it as a projective, as a vector, eventually I'll get P1. If I take Y, which will be 0, 1, 0, 0, and multiply it by this projection matrix, it will get B2, and the same with this. This is why the image of the x-axis will be P1, the image of the y-axis will be P2, the image of the z-axis will be P3. So this is, make it simple to understand this, or pretty much every one of them will be practically a point in the image plane. Now, if we think about what's the notion of these kind of like the rows of the P. So we saw how the columns of P represent the images of the X and the Y and the Z axis. So the rows is actually represent a particular world planes. So if we think about this as kind of like this X and Y, if we think about them, or let us think about the idea of the equation of a plane in the 3D space is actually an equation of a normal. So, oh, we don't have a board here, yes? Okay. So if, let us assume this normal will be represented as A, B, C, and 1 in the 3D space. So the equation, this is practically represent the equation of all the infinite planes which are perpendicular to this normal, which is their equation will be x, xa, yb, and cz plus d, and d will determine the elevation of this. Now, if if we think about this normal, if we have two vectors here, we can very easily represent this normal as a cross product of these two vectors. Yes? And the same thing, if we think about this practically representation, we will get the normal, which is practically, if this is the X and Y of the image plane, which is we have P2. This is the representation of the rows of the transformation matrix or the projection matrix. The same thing, if we take the P3, will give us the principal plane, which is parallel to the image plane. So what we will get the representation of a matrix as a column and row give us kind of some characteristic of the camera. This is why we often tend to write them as column and rows instead of writing them as a one matrix. Why we need this kind of this eventually? Because we always or often when we think about a image geometry or try to extract geometry from images, it's opposite from graphics. In graphics, we have the projective matrix in hand. We actually create the projective matrix, which is take the world coordinates and create an image. this is not the case when we actually deal with images from the real world. We have the image, we don't know the real world. We try to get information about the real world from the images. So often we do some computation, and depends what parameters or what information we want to get from images, which is where we can, for example, emphasize, or when we can do more computation. So if I'm only interested in, for example, some measurement in the image, I maybe don't need entire kind of to calibrate the entire camera. I maybe need some kind of several points will give me the information. So this is one of the issues, which is we look into the anatomy of the camera, which is practically into the projection matrix. Now, the principal point, as we mentioned, it's the intersection of the principal axis with the image plane. This is the principal point. It exists in the image plane. Usually, this is the point which is, if we see it as in the center of the image. If we look at this, is practically the center of the image. And this is, if we think about this, we also have what we call the principal plane, which is parallel to the image plane, but passes or exists at the origin. So if we think about, this is the principal point, let us call it x0, the intersection of the principal axis and the image plane. And then if we think about this, the representation of this P31, this is the P3 in the image. And then what we can actually get the x0 as the transformation of the point, or the row B3 with the transformation matrix. And this is what we will actually call it as the M3, M3 multiplied by M, where the M3 is the third row of the matrix M, which is the transformation matrix. And this is how we actually, if we can write this as the P, which will be written as M, which is 3 vectors, 3 rows vectors, and the point P4, which is the point in case will be 0, 0, 1 or 0, 0, 0, 0, depends on the type of the camera. Any question? Okay. So if we think about the principal axis vector, and this is what we mentioned about the rows of the camera. So we have, like when we looked at the camera and see, we have the 3 axes, how they are projected or how they are represented in the camera matrix. Now, one of the issue when it is we coming to projection, theoretically from the mathematical point of view, points could be behind or in front of the image plane will be projected to the same image plane because of the kind of the projection of the line doesn't matter if it's in front of the camera and back of the camera. This is from the theoretical perspective, but practically we are only interested in the half point of the world, only on those points which are in front of the camera. We are not interested in the, from practical point of view, in kind of points which is behind the camera. Now, and because of that, we are very much interested to know where is the direction of the camera, because the projection matrix, and does not really give us the notion where is the front of the camera. The only difference will be between them will be plus and minus, it's just kind of a sign. But it depends on the camera parameters to know which one corresponds to front of the camera and which one corresponds to the back of the camera. But if we think about like a projection of a 3D point in the image plane, and this is now, let us look at the camera as the x coordinate of the camera, and this is the equation we wrote before. So this is, we can write it as this, and now if we take now a point, which is, if we take the determinant of the matrix M, which is eventually give us scalar value, and multiplied by the M3, which is the third row of the matrix, and this is will give us 0, 0, 1 in this case. And this vector will represent the front of the camera. Now, this vector may not be represented like normalized in this case. This is the ideal case because we don't take much parameters. But the determinant of the matrix M will be 1 only if it's normalized. Yes, and there's another parameters which is, in this case, this is what we will get for the canonical matrix, which is mean that we have the camera facing, the camera is at the origin, and this is will be kind of the vector which is facing the positive Z. This is the camera, which is, in this case, will be the front. Is that clear? Now, and this is, and then in this case, the camera point coordinate, we can actually write them as the K, pretty much, which is this is the point in the camera coordinate, and this is what we will have the K4B, V. And if we think about this, we can now write this in completely kind of different order, where we, in this case, will know what's the direction of the camera. So if we write the transformation, this is what we have. This is the transformation. The only thing which is we added the K, which is will determine front or back of the camera. And this is will be MP4, as we mentioned earlier. And this is, if we think about the value that determine where is the camera, where is the front of the camera, will be the determinant of M multiplied by M3, just as we mentioned earlier. That's clear? So we now know all the parameters, including where is the front of the camera and where is the back of the camera. It's often the case that we do some kind of numerical analysis and get some solution, and we will find points which is behind the camera and point which front of the camera. And in case we know how to rule out points which are behind the camera, because they are just a mathematical solution, but they are not of a practical kind of use for us. So this is why we need to know which point behind and which point in front of the camera. Is that clear? That clear? Any question? Okay. Okay. Now, like what we have often, what we will get what we called forward projection or forward project. So what we have two cases where we do the projection of a point, a 3-point plan. So what we have 3D point, the normal case of the projection. We have what we called in computer graphics, we have a point in the 3D world. We know the projection matrix, and we do the projection, and we get a point in the image plane. So this is one case. This is what we called the forward projection, which is a pretty much a simple case. And if we think about this is what we will get for this is X. This is, if we call this, right, this point D, let's assume any point we want it to be D, which is we called a vanishing point. We could represent it as M P4, or eventually it'll be M big multiplied by D. And this is how we represent vanishing point. A vanishing point where several lines projected or intersect in a point. In a back projection, practically the only thing we know that we have an image, and in this case, and we have the center of the image, which is the vanishing point. This is the camera center. And this is, in this case, we need to resolve the equation PC equals 0 in order to determine C. And in the same times, what we usually if we think about, like, if this case we need to do kind of inverse for the projection camera, the projection matrix. And it's, since the projection matrix not necessary, or it's actually 3 by 4 and not 3 by 3 or 4 by 4, in this case we replace the inverse of the matrix, but what called the pseudo-inverse. Pseudo-inverse, it's pretty much very mathematically defined, which is the matrix which is multiplied by P will give us 1. This is how it's defined. So if we think about this as case, the pseudo-inverse, which is usually P plus, which is pretty much what we call, we take the P transpose multiplied by P PT transpose. And this is minus, which is, this is how we can resolve this. Or we can write this as in a simpler form, which is mean P multiplied by pseudo-inverse will give us the unit matrix, or the one in this case. So, and in this case, what we will, if we think about this as all the points, this is what we will see. This is, since this is not really, since a point, the solution will not give us often one point, it will give us infinite point along the line that connecting X with the center of the camera. And this is exactly what we are resolving here. It's not one point, it's actually a line. And this is how we know that this is the projection. Eventually, the inverse projection will not give us a 1 point, kind of, not, or like, not as in the forward projection, we know the 3D coordinate point will give us a 1 point in the image plane. Here we have 1 point in the image plane, and which actually could correspond to many points in the world coordinate. Okay, this is pretty much the kind of very like simple mathematic notation, which is we take the line here and actually multiply it kind of by the camera matrix. Is that clear? Any question? Okay. So there is another term which is we use, which is called the depth of a point, which is, if we think about what we called before, if we think, let us think about the column 3 of the matrix multiplied by a point X. And this is, since we have in this point 3, we have the X and the translation of the camera, we actually could write it as M3 because all the other value will be 0. And we also know that PC equals 0. Now, if we know that the determinant is bigger than 0, it's, for example, we often, like try to get the determinant of the matrix to be normalized, but it also could be either plus or minus 1, because if we don't do the normalization, then M3 will be kind of a unit vector in the positive direction. And then we define the depth, or easy to know that the depth, very easy mathematics kind of notation. So if we take this, the depth of a point X with respect to a projection P will be the sign of the determinant of M multiplied by the vector W there in top, which is we have actually divided by the length of M3 multiplied by T, which is pretty much very easy to see this based on the similarity of the two triangles, the triangle which is the small one and the big one. Any question? Okay. Now, what we will be able to get if we do this kind of like equation, what we will be able to resolve this kind of like matrix, and all this usually numerical analysis will give us, we'll be able to do some, if we have a point correspondence and we run our numerical solver, we will get usually a matrix, one matrix, and not really written as 2 or 3 matrices. So how we can get these matrices from these 2 or 3 matrices from one big matrix? Usually what we will do, we will use kind of what we called matrix decomposition. Matrix decomposition is a big field in many technique, which is take one matrix and decompose it into 2 matrices or more. Usually the common cases we decompose it into 2 or 3. Now why we want to decompose it into matrices with some properties. And this is how we will be able to do the decomposition efficiently. And we can use this kind of characteristics in order to kind of add meaning to these matrices. So if we do the kind of our numerical solution to these camera parameters or to this kind of equation, we get enough correspondence. What we will get one matrix M, and we are interested in the camera parameters, which is K, what we call the calibration matrix, and we are interested in the rotation matrix. We often want them to separate them because we don't want, if we want to apply or kind of do some computation which is only based on the camera calibration, we want to extract this from the rotation of the camera, because if we change the position of the camera, the rotation will be different matrix. Now the simplest or the best way is to do it is to use what we call the RQ decomposition. The RQ decomposition take matrix and subdivide it into 2 matrices. One will be upper triangle, and this is, and the remaining will be the matrix, the other matrix. So if we write this, in this case, what we will have M will be multiplied as a Q and R. Now, in this case, if we, this is take the inverse inside, what we will get the R minus 1 and the Q minus 1. These parts, will be the K, and will be the R, the other matrix. So this is how we will be able to get the calibration matrix from our computation. So if we think about this is, okay, and if we get S, as I mentioned earlier, not equal to 0 in our matrix, the K, because we get the upper triangle from the decomposition. If we get the upper triangle of the decomposition, we get the entire calibration matrix. But S, we expect S to be 0. If S is not 0, it means that there is a skew in the CMOS, which is very rare, unless we have problem with the optics or the CMOS. This is what we will have the calibration matrix. Okay. I think I have some. Okay, no, maybe. Okay, so one thing which is what we will have, this is the issue how we can get the camera calibration matrix we mentioned, but how we can get the calibration matrix. It's often the case that we do the calibration by computing, taking a word coordinate point and get their correspondence images in the image plane. Usually, we want this to be automatic, which is mean we don't this point correspond to this point, but we want something which is we can compute the correspondence from one image. In this case, we use what we called a calibration pattern, which is a pattern which is we have a knowledge about. We have a knowledge about which is mean either it's include usually lines that we can extract very easy, and these lines have some property which is that we expect if they are perpendicular. In the last lecture we see we can recover the projective transformation if we have like if we have lines, which is if we have a 6 points with correspondence, or if we have a 3 lines with correspondence, or 6 lines with correspondence, sorry, because every point eventually will be in the projective space will be dual to a line. Line and point are dual in the projective space. We can move from one to the other. So if we have something like this, we take a photo of this, and then what we can do, we need to get these lines. So one important thing is we know the angle between this plane and this plane, because this is by itself, one is not enough. So if we take an image, what we can do to extract lines and points. So let us look into what we want to solve. So now, if we get this pattern and we can find the correspondence, eventually our problem will be we have multiple images and we have correspondence between points, either in the correspondence between a point in the image plane and the world coordinate, or in multiple image planes. Any of them is enough to enable us or to enable recovering the calibration matrix. Is that clear? Because in the last lectures, we said that we can do the projective recover, the projective transformation, and we saw the projective transformation could be either corresponds between a two projective plan, which is we can actually apply a projective transformation that take correspondence points from one plan to another plan, but they should be generated with property which is similar to what we call imaging, or from a 3D world coordinate and image plane. Any of these will be, any correspondence like this will enable recovering a projective transformation. So now what we want to solve, we are looking for P. Here is very simple what I mentioned there. I have a point xi and the correspondence point x small. Now, one thing which is this is not easy to, the issue which is always in optimization or in solution, we want something to be 0, because it's easy to solve equation when we have in one side 0, because any point which is up to scale factor, we saw many points along the line will be projective to the same points, or practically the image of this word and this image will be the same point, the same correspondence, yes? Which is mean we can recover the projective transformation or the calibration matrix up to scale factor. This is what makes it quite complicated to do this computation, which is mean eventually we get two vectors which have the same direction, but they don't have the same value. So how we can resolve this if they have the same direction, but they don't have the same length? What? Normalization. Again, I will get a normalized factor, which is mean I need kind of like will not help me much to solve the problem. I need to get into equation which is often something which is guarantee that these two vectors are having the same direction before even normalizing them, because I don't know if I can normalizing them and I can do something and then compare them, which could be a good kind of like solution, but that will kind of make the numerical solution quite complicated. But think about if we have what really the operation that of two vectors pointing to the same direction will give us 0. Cross product of two vectors which is pointing to the same direction but different in the magnitude will give us 0, yes? Because the cross product of two vectors will give us the magnitude of the first one multiplied by the magnitude of the second one multiplied by sinus the angle between them. And then the angle would be 0, and this is why this value will be 0. In this case, which is mean that xi multiplied by pxi will be 0. If I look for the solution of this is what will give me the easy kind of like equation system. So for each point will contribute exactly, I wrote it now xi, yi as kind of like a, just to simplify this, and wrote it as this matrix. And this is the matrix which is I'm looking for. I'm looking for P1, P2, P3. Practically what we said earlier, these three equations are not linearly independent. One of them is linear combination of the other two. Kind of, if we just kind of easy to see that. And this is why after simplification, we get to the two matrices. Now, two equations per point, correspondence point. So, and this, what we will get, if we have 6 points, we'll get a solution for this. And this is how we can get a solution. So if we have, in this case, since we have 11 degrees of freedom, we can have, which is mean we need 5.5 points, but practically we need 6 points and more. So if we have 6 points, we can get a solution, exact solution. It's often the case that our like points we extract from the calibration are not accurate, which is mean we cannot rely on only 6 points, because these 6 points may not be the best we can do. So this is what we will often, we will get more than 6 points. But not only this, we want 6 points, which is somehow, we want them not to be what we called degenerate points. Because if we have 6 points that, for example, if 3 points along the same line, they are not independent. So this will create us a problem. So we need a point, 6 points, which is independent 6 points. For example, again, if we have a line and 3 points along this line, 1 point could be written as a linear combination of the other two. So this is, but usually since we have many points and they are not exactly accurate, we want to find a solution which will not be exact. If we pick a 6 points, any 6 points from our data set and compute the matrix, what's the problem with this?
You'll have more data than you actually need.
What?
You'll have redundancy.
If I have, let us, I have maybe 100 points, which is I get from like like computing the correspondence between the calibration pattern and the image. Now, I have 106 are enough for me to get the projection matrix. So I compute this projection matrix, I'm done. What's the problem with this?
You don't have an exact solution, but multiple solutions.
We have a, no, if 6 points are independent, I will get an exact solution.
But you've got more than 6.
I get more than 6.
So you'll have more than, you'll have 100 solutions.
Okay, let me ask, if all these points are accurate, the correspondence are 100% accurate, any 6 point I will get will give me the same matrix up to scale factor, yes? And this will be, in this case, any 6 I pick will be good. But in reality, we don't have this luxury of getting exact point. So we have measurement, and these measurements are not accurate. We have error. in these, and we don't know which 6 are the correct one. This is the big problem. We have 100 points, but we don't know. If we, by somehow an angel came and picked the 6 correct points, we are done. But we don't have, again, this luxury. So what we can do, if I pick 6 points and compute the projection, they may not be good for other points. So which solution I should get? So every 6 point will give me different metrics. I have, I don't know, like many matrices. Which one will be the best one? What? Not all of them will be the good, because if the, yes, not only because if these 6 points, let us assume I picked 3 of them where I get wrong measurement because my algorithm, I'll get this matrix will not be good for many other points. So I want the point which is pretty much have the minimum error, which is mean if I compute this matrix, and now I'm going to test this matrix, take every original point in the 3D space, make the projection, compare this with its image in the image plane, and then measure the distance between them. I would like to get the one which has the overall kind of a small error. So now we facing like 2 issues. One is how to compute this matrix, because I'm not going to pick 6 and compute this for 100, because will be enormous, and then pick the one which is the best. We want something to be able to compromise with. We want some solution which is good enough for us, but we need to know how to measure its accuracy, which is mean how to measure the error. Now, one thing which will be, if this is the image of the point which is, I want to see how far is this will be kind of from my point. So I maybe don't want kind of to pick points which are close, just to try to kind of get points which are different. So there is quite a like easy solution, or not really an easy, but it's, you plug it to any numerical solution, this kind of points, and try to minimize the error. You give the error, and it's actually try to minimize this error. Well, this is what's called the DLT algorithms, which is the linear transformation. I think we mentioned this in one of the lectures before or last week. So the DLT algorithm will give us a solution. Now we need to measure kind of the quality of the solution. Now we have 2 measures to do. One measure, which is we call the geometric, which is mean I have the 3D point in hand, apply the transformation, I get a point here. And the point which has correspondence is not exactly the same, it's a little bit different from it. So we have the geometric error, which is I can measure as the distance between these 2 points, which is all of us understand what's a geometric error, because we see it's the distance between these different. I can sum all these geometric error along all my points and see this is how I quantify the error, or take the average of them, whatever measure I decide. There is another error which is called the algebraic error, which is mean if I take the transformation which is I have from this point and compute algebraically the error only based on the multiplication of a vector by a matrix, and compute the error which is I will encounter, will be another value. So where this geometric error will come from? So practically we started by something we wanted to be 0. Yes? If we take this computation, which is take x, and then take the x big xi, multiplied by the matrix P, and then compute the cross product with the point which is supposed, or the corresponding point, and then we will not get 0. We get some value because we have an error there, yes? This is what we call the algebraic error. Is that clear? One thing which is, we know the geometric error, we know how to quantify the distance, because we know the distance. Here is the point which is I supposed to get this point, I get this point, so I know, like, I can compute the Euclidean distance, I can compute, for example, Manhattan distance, whatever distance I can compute, and I can have a notion about how far they are from each other. The algebraic, it's not easy to have a feeling about how much big is the error, yes? Practically, it could be various numbers. It's not that necessarily corresponds to the geometric error. But computing the geometric error is quite complicated, because I need to do the projection, then compute the distance according to the distance metric, and this plug it into my solver. Not easy. The algebraic error is very easy to compute. I just minimize this multiplication. So this is what we have, the dilemma between the geometric and the algebraic error. There is a kind of a measure, which is, I will stop in a few minutes, and then in the next, which is, I think in the last lecture we have gone over what we call the Simpson error, or the Simpson metric, which is, it's between them, which is mean it's easy to compromise, it is easy to compute, it is not as easy as the algebraic, but we have its kind of link or add algebraic notion to this, add geometric kind of explanation to this algebraic error, which is make us easy to understand and interpret. And in the same time, it's easy to compute. Is that clear? It's clear what's the difference between algebraic and the geometric, and why they are different. Why we would love to have only algebraic, because it's easy to compute. Many actually numerical analysis solution, you will optimize this function. It will be easy to optimize because it will be linear. The moment, if we think about it, if we are going to use, for example, Euclidean distance, which is simple. Sorry, we will jump from linear into quadratic, which is more complicated to solve and even harder to optimize. Questions? Okay, so I'll stop here. Next time I'll go over again the Simpson error, and then we'll go over some kind of in detail in the algorithm and see some kind of a example. And I think I will be, hopefully next lecture I'll be able to be done with a single image. Then we'll go into the dual image and computing the correspondence. We'll go over several general algorithms, how to compute the depth of a points based on images. We assume we have multiple images. I think I will go over only 2 images, and it's easy to, after that, extrapolate this into more images. And then we will look into kind of a general kind of technique, how these things are used. And after that, I think we can maybe move into kind of a reading group. So we'll see several papers and try to read and discuss together, which is, I think, after 3, maybe 4 lectures. I think 3 lectures most probably. If there is a need for 4, we'll do it, but I think at least these kind of basic kind of terminology will be in your mind that you'll be able to understand and criticize these papers. Okay? Okay, thank you, and see you next week.